All right, Courtney, it's just you and me right now. Can you hear me okay?
Yeah, I can.
Okay. So my plan is I was going to just go through a number of problems today. The first kind of couple are going to be likened to the kinds of problems you're going to see on the quiz. So just reminding everybody again, let me go to this slide again. This was a slide that I had up in class today. But just reminding everybody for your stoichiometry quiz, okay, your stoichiometry quiz for Friday, you are going to be given an equation. It will be a specific equation, not a generic equation like this, but it will be balanced, and you will be provided molecular weights for all species that are in the equation. You're going to need to know which ones you may or may not need to use. You will be given the mass of one substance, and you're going to be asked to tell me information about another substance that's in the balanced chemical equation. So for example, with the red line here, you might be given a mass of one reactant, and I'm going to ask you how much product could be made from that amount of reactant. Now, because I'm only giving you quantities of one reactant, that's kind of one of those kind of a little red flags that indicates, hey, this is not a limiting reactant problem because I only have information about one of the reactants. But I might be giving you information about one reactant, and then I'm going to ask you how much of the other reactant do I need to have in order to fully react with that amount of initial reactant that I have. So I can ask, for example, if I give you information about A, I can ask how much B would be used up, how much C would be made, or how much D would be made. Okay, so all kinds of relationships that we can have here. So all kinds of different ways for me to make different permutations of a problem. But that's going to be your stoichiometry quiz on Friday. It will be administered right at the start of class via Blackboard. So make sure to have, I think you can still access the quiz easily enough with your phone to enter in the answer for that. Now we are going to work through some other kinds of problems, stoichiometry specific problems. Tonight, we're going to work through some limiting reactant problems. And just to highlight and remind people that even though most of the time in these problem solving sessions, we're focused on kind of fine tuning your skills with sort of the main thing that you're going to see on a quiz. So for this case, it's stoichiometry. There still were other things that were important for Unit 3. So for example, let me just kind of go back through here and look at, and sometimes these skills kind of become embedded. So for example, stoichiometry was skill 3.3. So there was two skills that came before that. The first skill was the mole in chemical formulas. So it was, those were things that we learned about, how to use the mole, interconvert grams and moles, interconvert grams and number of items with Avogadro's number. So we learned about that with that first skill. But again, that sort of becomes embedded in the stoichiometry piece. And then balancing equations. So that's another important skill, is learning how to balance chemical equations, but highlighting for the stoichiometry problem you're going to see in class. I'm going to be giving you a balanced chemical equation, and I will be giving you molecular weights. So you won't have to worry about calculating those. But when we see a question on an exam, for example, you might have to put all of those pieces together. And we've done a couple problems like that. You may even need to take a chemical name and make it into the formula, make the chemical equation, balance the chemical equation, figure out the atomic masses, and then do the stoichiometry. So then we've got limiting reactant problems, which again, we learned on Monday and we continued to practice today. But the new thing, just to kind of refresh your memory, that we learned today is rather than being given masses of a substance, we're given volumes of a substance. So rather than using a molecular weight to convert to moles, if you're given a volume of a substance, if you know its concentration in molarity, that's the way to walk to moles with the information we had from today. Okay, so just kind of a big picture overview of Unit 3, okay? But the skill that you're going to see on Thursday or Friday's quiz is going to be this kind of level 1 stoichiometry, if you will. But we're still going to work through these level 2 limiting reactant problems today. And then what I'd like to do, we'll kind of see where we're at. I'd still like to spend some time, and I will go through, and this way it'll be recorded if anybody wants to watch it later. I will go through the the answer key for the first exam. So if anybody has any questions, you can kind of take a look at that. All right, so let me come back here to our first problem here on unit conversion. I'm sorry, on stoichiometry. I will say that we are going to have some more time on Friday after our quiz that I will go through some of the problems that we maybe didn't fully finish up. We'll kind of revisit those and take a look at those. So Courtney, before we start here, do you have any questions for me?
For the quiz, do we have to put units or no?
Well, so if the problem is you're rarely going to have a value that you provide as an answer that doesn't have at least a unit, if not even a qualifier. Remember, every time we talk about quantities in chemistry, you should think about three parts. You should think about a value, which is the number piece. You should think about the unit. And for this Friday's quiz, I've already sort of given you a heads up. You're going to be asked to determine a mass of something. So you're going to need to know a value, a mass, and a qualifier. Now, hang on just for a second, because maybe your question was, well, what do we need to put into Blackboard? You do not need to put anything into Blackboard except for the value. So, and I'll make sure to mention that on Friday. I want you to know what it would be, but it's not anything you're going to need to know for Friday's quiz. So for Friday's quiz, it's just the numerical value, because that's what you need to put into Blackboard. Anything else? Did that answer your question?
Yeah, it did.
Okay, well, let's go ahead and get started. And Courtney, it is all you today. So I have about 5 problems that we could go through. And so what we'll do is I've got the answers sort of available for each of these. So I'll keep an eye on the chat here, or because it's just you, if you want to just kind of unmute your mic when you're done and just let me know whether you're done, meaning you got the right answers to this problem, or you're ready to walk through the solution because you got stuck and you didn't get these answers. So always how I like to run these problem solving sessions, since we have some additional time. And I think it is really important for you guys. I know we talked about in class today the desire to have me demonstrate problems, which is, I think, a great step in learning. But this is probably even a more critical skill, is you trying problems on your own, but having the ability to work with me or a tutor, or however it works, so that you can get feedback when you get stuck to kind of help get you out of a bottleneck you might be in. So I'm going to let you work, Courtney. Just let me know when you're done and we'll work through the solution.
Okay, sounds good. Can we go over if I got the balanced equation correct before I do anything further?
Absolutely. I think that's actually my next slide here. Well, don't look at the bottom part, but there's the coefficients are 1, 8, 5, and 6. Is that what you got?
Yes, it is.
All right. Well, I'm going to flip away from that slide to kind of let you work on that.
All right, thank you. All right, I'm a little stuck on the second one. If we can go over that a little bit.
Sure. All right. So, and I'm probably going to, even if it's a problem you may have gotten, I'm still going to go through sort of the same level I would if somebody didn't get it, just so that anybody who's watching can kind of get some direction. So 3 parts to this problem, right? Balance the equation is the first part. And I'm glad you asked on that, because it is one of those things. If you don't have the right balanced chemical equation, your stoichiometry is going to be off. So that's why, again, for Friday's quiz, I'm not testing you on, can you balance a chemical equation? I'm not testing you on, can you determine molecular weights? I want to know, can you do stoichiometry? Okay. So once you balance the chemical equation, then that allows us to use this information and say, when we have 4.62 moles of oxygen that's reacting, how many moles of water will be made? So let's kind of go through that solution. I've got this on 2 separate slides here. So here's the first part, right? This is actually, if we think about, let me just kind of give you a highlight here. If we think about what you're going to have to do, this first part is really just kind of going through this leg, right? If we want to think about there being different legs or different steps to our problem, your quiz for Friday is going to be a 3-step kind of situation. You're going to have to do grams to moles, then your equation to do moles to moles, and then back again to grams. So this problem that we're just working on here is really, let me just highlight here. This is really just looking at this first part, or I'm sorry, this middle part right here, this moles to moles. So let's go back here. And so we've got, in this case, we use our balanced chemical equations and the coefficients from that balanced chemical equation to change who we're talking about. And so in this case, if we've got 4.62 moles of oxygen, we're going to make 3.47 moles of water. Okay, so any questions on that one, Courtney?
So I'm kind of like, because I'm still like studying the steps and stuff. So I'm like kind of looking at my notebook. So the one problem we did in class, we went from like the sodium.
Yeah, so tell me what problem it is and I'll pull it up here and then we can look at it.
It's the sodium hydroxide solid reacts with carbon dioxide gas.
Yep, so I've got that one right here. Yep.
So why wouldn't we, like, could we still go in those same steps, or is that going to make our answer off?
So yes, except this problem was actually, this problem is more likened to the kinds of stoichiometry you're going to need to do with the quiz, where you're going to start with a mass that you then need to go to moles. Then you use your balanced chemical equation to change who you're talking about. And then you go from moles to grams using molecular weight. The problem that we just did like 30 seconds ago, the new one, all that we were doing was doing this intermediate step, because what was given to you was not a mass. What was given to you was a mole. So you kind of started halfway down the path, if you will. Okay. Does that make sense?
Yeah, that makes sense now.
Okay. So, and remember that you're going to hear me say this a lot in class, the level of difficulty that you have with problems is proportional to how directly information is provided to you. So this problem is actually, for this B part, the second part is simpler than you're going to see on your quiz, because it's only one step. Because if we were doing a 3-step stoichiometry problem on Friday, I already did step 1 for you, because we're starting at moles of oxygen. So all you need to do is use your balanced chemical equation to change who you're talking about. And this problem doesn't ask you to then convert that moles to grams. So it's only one unit conversion step in that process. Does that make sense?
Yeah, that makes more sense now.
Okay, so let's go through this next part, because I know you said you got stuck a little bit. So this is asking us how many molecules. So I'm going to put you on the spot a little bit and say, if you see something that's saying how many of something, what should you be thinking about in terms of a special quantity that you want to be using in your calculation? Do you know?
Would it be the limiting reaction?
Well, a limiting reactant problem, that we're only going to think limiting reactant, like if they gave us quantities of both of these pieces. Okay. But if you see the words, how many, we're talking about the number of items that we have. What is that indicating that there's a special unit conversion we're going to want to use?
I'm looking.
I'm going to put something up here to sort of help you. So this is kind of the summary of everything we learned in Unit 3 here, all the kinds of different unit conversion pieces that we're learning about. Do you see the one here that allows us to talk about the number of things that we have?
Avogadro's number.
Yeah, Avogadro's number. So that number will always be provided for you. You don't need to remember it, but it's one of those things you need to know how and when to use it. So if we see something that talks about how many items, that should be a red flag that, hey, we want to be thinking about using Avogadro's number. Okay. Or if we're talking about specific numbers of molecules and so forth. So now we want to know how many molecules of this guy are we going to need to produce this number of molecules of CO2. So this is a little bit There's going to be more steps to this unit conversion. But if I were to sit here and I'm just going to use my highlighter to kind of map on here, now they're telling me that I want to make 2.31 times 10 to the 24th molecules of CO2. So that's what I want to make here. And the question is, they want to know how many molecules of this guy am I going to need? So how many molecules? So I'm going to be doing a unit conversion here, but rather than going, so again, your quiz, and I actually talked to Sarah, one of the Sarahs in class today about this. The more that you can sort of see how a lot of these problems are related, the easier things are going to be, because if all of a sudden you just see every problem as, oh my gosh, that's just a brand new problem, it can get overwhelming. But if you see the relationship between these, so for example, the problems that we did on Monday were grams to moles using molecular weight, moles to moles using chemical equation, and then moles to grams using molecular weight. Okay. Today, we did volume to moles using molarity. Now, what's the same is moles to moles using balanced chemical equation. And then we went from moles to volume using molarity. This problem that we're doing right now is going to go from number of molecules to moles using Avogadro's number, moles to moles using chemical equation, that's the same, and then moles to number of molecules using Avogadro's number again. So we've got kind of 3 different kinds of problems, but they're all on the same sort of theme. So let me come back here just to this kind of relationship again. This is like the common thread between them. But maybe we'd go from number of molecules to moles using Avogadro's number. Maybe we'd go from volume to moles using molarity. But that central piece is the same. So the more that you can kind of see the similarities with the different kinds of problems and see how many of these things are what we call a variation on a theme, okay? It's going to make your life easier, because then you'll see the patterns that we have with these. Okay. So let's go through the answer then to this problem, right? So here I have that walk. I sort of mapped it out in my highlighter here, but noting here we've got, they tell us the number of molecules of CO2 we have. I can use Avogadro's number to get to number of moles. And then I can use my balanced chemical equation to change who I'm talking about and change from moles of CO2 to moles of C5H12. And then again, I'm going to use Avogadro's number to get to number of molecules. Okay, so here's this roadmap put into action. I've got this number of moles or molecules of C5H12. Okay, and I probably should put, I harp on you guys and say we want to make sure that we always have values, units, and qualifiers. So I'm going to put that in, that this is the value, the number that we have of the number of molecules, the unit is molecules, and then the qualifier that belongs to C5H12. Okay, Avogadro's number here, 6.022 times 10 to the 23rd. Again, make sure that you are competent putting that in correctly in your calculator. Run through these calculations if you're just following with the video later to make sure that you get mathematically the same answer in your calculator, because otherwise there could be something wrong with how you're entering things into your calculator. Balanced chemical equation and my coefficients here allow me to change who I'm talking about. And then I'm going to do Avogadro's number again to allow me to change back to molecules. So, Courtney, where were you stuck?
I guess I was just mainly confused, like how to start it. At first, but like now it makes like more sense to me.
Okay, and I'm gonna put something else up here. I just kind of want to highlight like how to think about these things. So I'm going to put up like a generic equation, right? We're going to have some way of saying that I've got something, some quantity of A. So it could be grams, it could be molecules, or it could be a volume. With all of these, I need to ultimately get to the number of moles that I have, right? So using, if I'm starting with grams, I'm going to use molecular weight to get to moles. If I'm starting with molecules, I'm going to use Avogadro's number. And if I'm starting with milliliters, I'm going to use molarity to get there. So I can give you the starting piece. Now, this is not going to be the case for your quiz on Friday. I already told you it's going to be grams, and then you're going to need molecular weight to get to moles. This is sort of the common piece, changing who we're talking about, but remembering I can relate this to any one of those 3 other pieces in my equation. And then beyond that, I can ask in my problem, do I want to know grams in my answer? Do I want to know molecules in my answer? Do I want to know volume in my answer? But again, going back to from moles to something else, if I want to go to grams, I'd use molecular weight. If I want to go to number of molecules, I'd use Avogadro's number. If I want to go back to a volume, I need to know molarity. So maybe you can already see from just what I'm putting here, I could have one single equation that I could probably create hundreds of different permutations of problems from. But if you see this theme, I need to walk to moles because that's the only kind of common language I have to be able to compare things. It's an apples to apples comparison. So this is sort of the common piece that we always are going to have here. So this is a common thread. Okay, and we need to have a balanced chemical equation in order to be able to use this piece. So does that kind of help kind of see a big picture view of it, Courtney?
Yeah, that you doing that chart like helped a lot. I took a picture of it too, so I have it.
Okay.
But yeah, that helps a lot to know where what form to use when dealing with certain things.
Right. And so you guys know your quiz on Friday is you're going to be given a mass, use molecular weight to get to moles, use your balanced chemical equation to change who you're talking about, and then use molecular weight again to get to grams. Okay. I want to know on Friday that you can do basic stoichiometry. Now, how this becomes kind of leveled up, if you will, is maybe I start with a volume of something and you use molarity to get here. But at the end of the day, I might want to know the mass of a product that you get. So we can interconvert these. And not for Friday's quiz, but fair game for something that you might see on an exam. And then we're going to move on in a little bit. We can do limiting reactant problems. And that's where you end up having sort of multiple reactants that you start with, or quantities of multiple reactants. That's kind of a red flag that you've got a limiting reactant problem. All right, any other questions on this guy then?
I'm good.
Okay, all right, so let's work through another one here. And I'm crossing off the A part here because it actually is not, it's one step away from being B. So let's just take this all the way to the end. We've got a substance here that we've got potassium nitrate kind of doing a decomposition reaction. So this is, if you want to like kind of mark down problems that are like, hey, this is like what I might see on the quiz. This is an example of one. I give you a balanced chemical equation. The only thing that's not part here is kind of having the molecular formulas. So let me actually, Courtney, I'm going to put in the chat here and I'm going to let everybody know. I put this as a link on Blackboard. There's a great website that I go to all the time. It's just a super easy website to figure out molecular weights. So let me put that link in the chat for you. I'll tell everybody else. It's available under the resources tab on Blackboard. My computer is really slow. Am I laggy at all for you, or am I okay?
You're okay on my end.
Okay, good. I think my computer just doesn't like having as many browser tabs open as I do. So it's taking me a minute here to get to the Blackboard site here to copy this link. So why don't you start trying to work on this problem? I'm going to continue to find this link. I'll put this link in the chat for you, and it'll just be a nice way that you can really quickly get the molecular weights that you might need to have to work through a problem.
All right, I'm ready to go over it.
All right, sorry, my computer, like it's taking forever for me to navigate between things. And I'm sorry, I didn't get a chance to post that link. I'm getting this comment saying my internet is unstable. So hopefully I'm not too laggy here. Did you get the right answer?
So I'm kind of lost in steps again.
Okay. So, and the hope is the more problems you do of these, it's like when you start learning a foreign language, the first time you're hearing things, like it takes so long to sort of process information, and then it takes a while. But then the more times you see something, and you see these patterns, it kind of just sticks more. All right, so let's walk through this problem. So steps that I want you to have so that we sort of make sure, if you're not certain where to start, always start with the same things. Start with a balanced chemical equation. Now, again, for your quiz on Friday, it's going to be provided for you. So for this one, totally provided for you. What I always like to do is I like to use my balanced chemical equation as a way to sort of organize pieces of information, because that allows me to sort of create a roadmap. Okay. Am I kind of getting glitchy? Because I'm watching my video and it seems to be like not great. Am I okay still?
I'm a little bit glitchy, yeah.
Okay, all right. So hopefully this will be okay. Let me know if it gets really bad, and what I might do is try to restart my computer and sign back in. And as long as you stay there, the recording will keep going. And then we'll be good. But let me know if for some reason, just interrupt me if for some reason it starts getting bad. I was trying to quit things on my computer, but it's like so slow right now, I can't even quit things. All right, so I have a balanced chemical equation, and I like to use that as a way to organize the information that's provided. So it says I want to produce 56.6 kilograms of oxygen. So I'm going to put that piece over there because that's a piece of information that's given to me. And the question says, I want to know how many grams of potassium nitrate must I heat? So in red, I've written down information that's provided in the problem, information that's given to me, and then from the prompt, what I want to figure out. Now, once I have that piece, those pieces of information down, then I have to say, how do I connect these two? And that's what unit conversion is about. How do I take information that I know and use it to go where I want? Okay. So in this case, and this is just like you're going to see on Friday's class, with the exception of the only thing that we don't have here is I will be giving you molecular weight, so you won't have to figure that out. So I'm going to take the mass of oxygen that I'd like to produce. I'm going to use molecular weight to convert it to moles. I'm going to have a balanced chemical equation to change who I'm talking about. And then I'm going to use molecular weight again to figure out how many grams of my reactant, potassium nitrate, that I'm going to use. So sometimes, and I'll walk through the solution in just a second here, but sometimes one of the problems that students have is this problem kind of goes in the reverse of how you think chemical reactions happen, right? It's not saying start with this much reactant and tell me how much product is being made. This is saying, I want to make this much product, tell me how much reactant I need. You know, back to our baking analogy, right? It's the equivalent of saying, I'd like to make 2 dozen cookies, right? Or 2 batches of cookies, let's say. How many eggs do I need? How many bags of chocolate chips do I need? So again, you're not always going to see a stoichiometry problem that's saying, starting with a reactant, go to product. You can be given information about a product and go to reactants, okay? So I'm going to pause there for a second, Courtney, and ask you if you have any questions. I think one of the most important things is writing the roadmap. And we talked about that in class today, where it's like, okay, I'll work with you guys in class to kind of create the roadmap, but then you guys execute the drive, do the math, do the calculations yourself. But I do think 90% of the problem is sometimes students knowing how to create the roadmap, the directions for the calculation that you're going to do. So I'm going to give you a moment to kind of ask questions or comment on kind of that first sort of planning phase.
Well, so after looking at it, I'm just stupid and made stupid mistakes.
No, tell me what you did.
So I had the correct roadmap, but instead of putting 5 moles of O2, I accidentally put 1 mole of O2.
So you were off. Okay.
Like off a little bit, yeah.
Yep. So, and that's one of the ways, especially if I'm giving you answers here, like always just take the answer and, like see what you're off by. And that can often be like one of those triggers, like as you're working through problems on your own, if you know what the answer is, see if you're off by some number that makes sense, whether it's a whole number. So you know it's something maybe to do in your kind of stoichiometry piece with coefficients, or maybe you used a wrong molecular weight, but you might be able to figure out where you went off if you sort of do that. But walking through this problem for anyone who is watching the video later and kind of needs some direction with this. So starting with information that I'm given, 56.6 kilograms of O2. Now, not written kind of in part of what I have on my roadmap is this idea that I first need to do a prefix conversion. Because remember, the units of molecular weight are grams per mole. I was given kilograms, so I need to convert this number of kilograms to grams. And I in all the years that I've taught general chemistry, I continue to see, students consistently putting the wrong, the 1,000 in the wrong place. So make sure that you know that we're always going to have the big number with the small units. So the 1,000 goes with the grams, the 1 goes with the kilograms. All of my units, when I do stoichiometry, I try to be super consistent and super anal about having values, units, and qualifiers, because that ensures that I don't miss something. Okay, so I've got grams of O2. So I'm going to have grams of O2 go away and get to moles. And then my balanced chemical equation allows me to change who I'm talking about. So moles of O2 will change to moles of KNO3. And then moles of KNO3 will go to grams of KNO3 using the molecular weight of potassium nitrate. Now, the only thing I didn't do here, and I have a little bit of a shortcut, and I'm just going to kind of highlight it here, that if I stopped my calculation just as I've shown here, I actually wouldn't have units of, or I would have units of grams, but I actually did a prefix conversion here to get this to be units of, actually, let me see here. Let me run through this. I may have just written down the wrong unit. 56.6 times 1,000 times 4 times 101 equals divided by. No, I think I just have the wrong units there. That should be grams. So 56.6. Let me just check my calculations again. Times 1,000 times 4 times 101.11. I thought maybe I had converted it to grams, but it is in grams. Times. Yep, this is my mistake. This should be grams. All right, so apologies, those of you who were kind of like working on and you were off by a factor of 1,000 and you didn't quite know where, apologies, that was just Dr. Parenti having the wrong number here. And this is actually in units of grams already. So we don't need to have this part. Sorry about that. All right, Courtney, any questions on this guy?
No, I'm good with this one.
Okay, so this example and then the one we just did, these are sort of classic examples of the kinds of problems that you're likely to see on Friday. So we might be doing some problems here that ask you to do some extra skills like balancing an equation. That's what we did in that first problem, or figuring out molecular weights. Those will not be part of what you have to do on Friday. You'll be given a balanced chemical equation. You'll be given molecular weights. You just have to know how to do the stoichiometry piece. Okay. All right. So here's another problem. I'll give you a minute to try this one. This one you do need to take. So what's different from this problem from what you'll see on Friday is this is one that's asking you to put together the chemical equation to balance it. Okay. And so you're going to need to do a little bit of nomenclature. Okay, so I'm going to let you work on this, Courtney, for a minute. Let me know when you're done, if you get the right answer, or let me know if you're ready to kind of walk through the solution. Courtney, you keep working here for a second. I'm going to disconnect my computer and try restarting it. It's really getting laggy, and I'm worried I'm going to end up having a problem in a little bit. So you keep working. I'll be back in just a moment.
Okay.
All right, so hopefully this is going to be better. You there, Courtney?
Yeah, I am.
How'd you do on this problem?
Can I just check my balanced equation so I can try and finish the problem?
Yep, so don't peek, but it's coefficients of 1, 10, and 4. So it's P4 plus 10 Cl2 plus it goes to 4 PCl5. Okay.
Yeah, thank you.
Yep.
Okay, I think I'm ready to go over it.
All right, my computer is so much happier now. I think I just had so much stuff open, it was not good. So did you get the right answer?
I keep getting like a bigger number.
Okay, so let's take a look at what we have here. So here's our balanced chemical equation, right? Which you said you did you have that right, or I know you wanted to check it?
I had the balanced equation right. I just wanted to check it.
Yep. So again, if I take information that's provided, that's going to create my roadmap. So they give me a mass of elemental phosphorus. I can use a molecular weight to get to moles. I can use my balanced chemical equation to change who I'm talking about. And then again, I can use a molecular weight to get to grams. Okay, so that's my walk that I'm going to have for my calculations. So then when I execute that and do my calculations, it's basically what we see here. I start with grams of P4. I'm going to use the atomic mass of P4 to change to moles. So kind of mapping on some things here. This is my molecular weight sort of unit conversion piece. This is my balanced chemical equation unit conversion piece. This is my molecular weight unit conversion piece. Okay, and then I end up having 2.6 times 10 to the third grams of Cl2. So talk to me about where maybe you got stuck. What was the answer that you had?
Well, so what I did is I think I just like interpreted the problem wrong.
Hmm.
I had the first few steps I had correct. But instead of putting the chlorine gas, I did the phosphorus pentachloride. So I like swapped.
So, and now you can see, I'm going to come back to this thing that you said you took a picture of before. You took a walk that went to here when the walk in the problem was really going here. And so you kind of, the first leg of your trip was right, but then you took a wrong turn in trying to actually take it to figure out the amount of product, when really I was asking the question, how much of the other reactant do I need in order to fully react that amount of reactant. So do you see that piece? And I think you see it now. Your walk went like this. So this part of your leg and that part of your leg would write, but rather than taking this walk here, you came over here and went over there.
Yeah, that's exactly what I did. But like, I know what I did now and how I messed it up.
Yep. So, and that is just part of trying to, look at the problem and make sure you have a roadmap that kind of connects here, right? I could easily write a problem that asks you to tell me how many grams of phosphorus pentachloride would be formed, right? And then your calculation would be right. So, and then it's tough if like you feel like you've got the right roadmap, but you wrote down the wrong roadmap from your from the prompt. And then if you kind of have taken that wrong turn in your map, it's hard to kind of come back out of it, even if you're checking your answer. So one of the things I just want to make sure to do now that my computer is kind of working easily here, I'm going to actually put that link for the molecular weight calculator in the chat here. And again, reminding everybody it's available on Blackboard, but I'll put it here for you, Courtney, and just so you can kind of click on it. This is just a website that you can go to that easily, you literally put in the molecular formula, hit calculate, and it gives you the molecular weight. All right. Questions on this one? Or are you ready for another?
I'm ready for another.
All right. So, well, let me ask you a question, Courtney, especially since you're the one who's here live and in person. We can move on. Now, this obviously is kind of moving into a different category. We're starting to talk about limiting reactant problems. So this is a problem that kind of walks us through how to think about determining a limiting reactant. So we could do this, or do you feel like you want to go over the exam? What do you feel like you want to do?
It's honestly fine with me. Like, more practice, the better, honestly.
Okay. So let's just keep doing these problems. So just to highlight, we're sort of switching away from the kinds of problems that you're going to see on the quiz. So this is related, it's still stoichiometry. It's still the same kinds of calculations, but remember limiting reactant problems. Let me kind of flip to this, going back to kind of my little slide here. Limiting reactant problems really are two sort of embedded level 1 problems. If we were to call these sort of level 1, right? Our level 2 problems, our limiting reactant problems really are like 2 combined level 1 problems, because in the problems you're going to see on Friday, it's just one walk, grams to moles, moles to moles, moles to grams. When we're doing limiting reactant problems and you're given quantities of 2 reactants, you have to take each one and go grams to moles, moles to moles. Now, you don't have to do the last moles to grams piece to be able to do the comparison, but you have to do at least a grams to moles and moles to mole, grams to moles and moles to mole for each one. And then you compare the number of moles of a common product that you make. You find out who makes less, and that's going to be your limiting reactant. And from that point on, all of your calculations are focused on that limiting quantity. Okay. So let's kind of go here, and I'll give you some time to sort of work on this first problem here, which is a limiting reactant problem. So to highlight, if you were to see a limiting reactant problem on an exam, it's possible that you might get this prompt up to kind of the A part, and I just might ask you the D part. A, B, and C are kind of like the intermediate steps along the way to getting to be able to answer D. So just keep that in mind as you're working on this. These all build, but this problem is designed to kind of walk you through the thought process of how you determine who the limiting reactant is, and then taking that guy on to do your calculations. Okay, so I'm going to pause for a second there on my end, and I'm going to let you go ahead and work on this one, Courtney. Okay.
All right, I'm ready to go over it. I'm just confused exactly where to start with it.
Okay, so we'll walk through this problem here. All right, so and again, I want you to always treat these problems the same way, because if you sort of have these step-by-step ways of thinking about things, it's sort of like a scaffold, like you know how to like walk from one step to the other. So the first thing I always want you to do is write a balanced chemical equation. In this case, that was given to you. Then take information from the problem. It's kind of write it underneath. So I know there's a lot that's here, so let's kind of take it one piece at a time. So up here is our balanced chemical equation. So take pieces from information that's provided and write it underneath. So it told me that I had 5.70 grams of my SRH2, my strontium hydride, and 4.75 grams of water. Now, the problem then asks, I'm going to flip back so we can just read the prompt. At the end of the day, we want to know how many grams of water we can produce. So depending on who I think is limiting, I can make different amounts of water. So the fact that we have two amounts of reactants that are given, that is our red flag. That's our sort of kind of, clue, if you will, that this is a limiting reactant problem. So how you do a limiting reactant problem is I do two sort of nested, embedded level 1 type problems. I'm going to do a water to hydrogen gas calculation. So grams to moles using molecular weight, change who I'm talking about using balanced chemical equation. And then I'm going to go ahead and do all the way through here because I'm going to need to know grams of H2 gas anyway. So I'm going to do, this is a fair problem for Friday's quiz. It's a mass to moles, moles to moles, moles to mass. Okay. Now I have to do this for my other reactant here. So I'm going to have grams to moles, moles to moles, moles to grams. Okay. So I need to do double the number of calculations that I have here. And then I'm going to say who makes less hydrogen gas. That is my limiting reactant. Okay. So in this problem here, I'm going to start with mass of strontium hydride. I use my molecular weight to get to moles of strontium hydride. I use my coefficients for my balanced chemical equation to change who I'm talking about. I use my molecular weight of my hydrogen to kind of get to mass of hydrogen. And if I have this much strontium hydride, I could make 0.256 grams of hydrogen gas. Now I need to do the exact same calculation with water. Okay, and I'll talk in a minute about why I crossed off this calculation in red. You need to do both of these calculations. So I've got a mass of water that I convert to moles of water using molecular weight. I use my balanced chemical equation to change who I'm talking about. And then I convert moles of H2 gas to grams of H2 gas. Now, if I had this much water to start with, I could make this many grams of hydrogen gas. Okay, so coming back to our kind of baking analogy in class, we talked about making batches of chocolate chip cookies. If you've got one bag of chocolate chips, I can only make one batch of cookies. If it takes 2 eggs to make a batch, but I've got a dozen eggs, I could make 6 batches of cookies with that dozen eggs. I'm not going to be able to make 6 batches of chocolate chip cookies because I only have one bag of chocolate chips. I am limited by that. So the same is true here. Even though I could make a larger amount of hydrogen gas using the amount of water that I have, this is equivalent to my eggs. I have more of it than I need. So I'm basically going to be saying that this guy is my limiting reactant. Now, what's really important here is what you do with this next piece, because there's a couple of common mistakes that students have. Sometimes students will say, oh, I'm going to add these two together. Don't add them together. That's the equivalent of saying we could make 7 batches of cookies using 1 bag of chocolate chips and a dozen eggs. Just because we could make 6 batches with our dozen eggs doesn't mean we're going to make that many batches of cookies. We are limited by the number of bags of chocolate chips. The same is true here. We are limited by the amount of strontium hydride. So this is the ultimate answer to the problem. So I'm going to pause for a minute there, Courtney, see if you have any questions. Hang on one second. I'm going to mute myself because I need to, there's a lot of background noise here. So hang on one second. All right, so go ahead, Courtney. Where did you get stuck, or how do you see with what you have now, how that kind of, fixes your understanding?
So as I was working on it, I had all of the correct steps. I just kept second guessing myself and thinking I was wrong.
Okay. So the only thing, so as part of this problem, you see how I wrote down these numbers that were here? I don't have those numbers on this problem. And part of it is when I was going through and I was making this kind of key for this problem, it's not common to kind of stop your calculation and sort of figure out moles. So if I had stopped kind of at this point and I figured out numbers of moles here, because look at, I would be figuring out moles of H2 and moles of H2. If I had stopped my calculations there and kind of went through and did that, that's how I get those answers. You could compare moles of the same product. Because remember, converting moles to grams, both of those numbers get scaled by the same factor. I'm multiplying both of them by 2.016. So that's how I'd kind of get those answers. And this came up in class today. I had a couple of students ask me afterwards, because when we did our limiting reactant calculation, I took each calculation from grams to moles, moles to moles, moles to grams. I went through all 3 steps. You don't have to go through all 3 steps. At minimum, you have to go through 2 steps. You have to go through grams to moles and then moles to moles, because I have to be comparing moles of the same product to figure out who's limiting. It's not a problem if you take each of them and go all the way through. And again, you're going to choose the one that makes the least amount of product. That guy is your limiting reactant, and the amount that limiting reactant makes is the answer to your problem. So any other questions or comments, Courtney?
No, I think I'm good. I understand the concept. I just need to stop second guessing myself. And I think that's just anxiety in me. That's like, nope, you're wrong. But in reality, I know what I'm doing.
Well, particularly if this is something new for people. I mean, there's a lot of steps to it. And I've noticed as I've kind of walked around and circulated with seeing things that people are doing, if you are still doing things with proportions, I want you to break that habit right now, because our unit conversion kinds of calculations are only going to get longer and more involved. And keep in mind, if you're doing proportions, each time you have one unit conversion step, that's a separate proportion calculation problem. So trying to do this with unit conversion, it's just 3 steps all the way through, okay, or 3 pieces all the way through. If you're to try to do this via proportions, you're doing 3 separate calculations, and it's real easy to get confused and lost in the weeds of where am I in my proportions calculations. So please, please, please make sure that you get comfortable. That's why it was like the key skill from unit 1 is knowing how to do unit conversion. All right, anything else with this one, Courtney?
No, I'm good.
All right. So here is another one. This one's a little bit involved. Okay. So what I'm going to do is I'm going to let you look at it for a minute, and then try to start writing the chemical equation. So highlighting, this is different from Friday, because as you're going to see, it's a limiting reactant problem. And this is one where you actually have to create the balanced chemical equation yourself. So what I'm going to do for you in a second is I'm going to stop sharing my screen, and then just so you don't kind of peek and see the next answer here. But what I'm going to do is I'm going to kind of put up the balanced chemical equation, and I'll put up the answer as well, so that you can kind of see if you're right. But try working on this limiting reactant problem. And just to highlight for everyone, as you're looking through these problems, as they are numbered here, these are the problems as they appear on your skills sheets. So skill 3.3 is stoichiometry. So these are the problems that you find at the end of the notes portion of those sheets. All right, Courtney, I did put up the balanced chemical equation there as well as the answer for you to kind of check your progress as you're sort of moving forward.
All right, I'm done.
All right, Courtney, I just saw that you put done in the chat there. So good. Done means you got the right answer, right?
Yeah.
Yay. Very good. All right. So I'm going to walk through this one just slowly for anybody else who's watching the video if you weren't able to sort of get the right answer. So this one, challenging on multiple levels. More challenging than you're going to see in your quiz, but on par with something you might see on our exam that we'll have right before fall break. So we always have to start with a balanced chemical equation. So what's challenging with this problem is the first thing that we needed to do was take words and make chemical formulas and then put those formulas together in an equation and then balance the chemical equation. So when we have that information, then I always like to put, again, information that's provided in the problem underneath the corresponding species in my balanced chemical equation. So it tells me I've got 60 grams of each of my reactants. And I want to know, again, be able to look at the question prompt and find the part that says, what am I looking for? What mass of carbon tetrafluoride? So that's what I want to figure out, mass of carbon tetrafluoride. Now, because I notice, and this is why it's helpful, if you write things kind of underneath an equation, if you write things underneath an equation, it's easy to see that, well, wait a minute, they give me quantities of 2 reactants. So that's a little bit more challenging to figure out how much product I make because it's a limiting reactant problem. So notice what I do here is I take each one of these and treat it as an independent stoichiometry calculation. Grams to moles, moles to moles. And again, you could compare just those moles here, but you could also go directly to grams with each of these and then pick the one that makes the least number of grams. And that's sort of what I did here. So here's if I started with 60 grams of cyanogen, which is CN, the quantity, there's 2 of those. So I use molecular weight to get to moles, my balanced chemical equation to change who I'm talking about, and then the molecular weight of CF4 to get the mass of CF4. I do the same calculation that I have here, but starting with that 60 grams of F2. Now going through molecular weight of F2 gets to moles, balanced chemical equation change is who I'm talking about. And then I've got my molecular weight there of CF4 to get to grams of CF4. Now I clearly make less CF4 using the 60 grams of F2 than if I were to use 60 grams of cyanogen. So that means this guy is my limiting reactant. And in reality, I didn't do it on this problem, but this calculation becomes irrelevant. I don't use it for calculating any answers to problems. I don't take and add that 202.96 to the 39 and change, but I need to make sure that I round this to the correct number of significant figures. So reminding you guys about significant figures. I've got 3 significant figures in the mass of my information that's provided. And so I want to have 3 significant figures in my answer. Now, with regards to significant figures on, exams and so forth, I always give you plus or minus 3 or 1 significant figure. So if we needed 3, you could answer it with 2, 3, or 4 significant figures and still get full credit. But if you do not have units or you do not have significant figures and you're off by more than plus or minus 1, you will lose some points for that. Okay, so Courtney, I don't think you need to kind of go through any questions there, or you might have some questions, but you said you got the right answer, but I'll pause for a second there and I'll see if there's anything else you wanted to ask, talk about with this specific problem.
No, I'm thinking I'm good, but like just when it says like, because it kind of confused me at first, but when it says like the 60 grams of each reactant is used, use both, do 2 different problems to figure out which one would be used.
Yes. So the fact that it says that I have 60 grams of each, that is my sort of, little clue there that this is a limiting reactant problem. So when you have a limiting reactant problem, you have to do 2 independent stoichiometry calculations. You take each reactant onto the same quantity of product. Now, highlighting again, you can stop at moles of product. Okay, you can stop there and compare those, but sometimes I just take it all the way on to grams anyway, only because the problem usually is asking you like what mass of product. So I'm going to need to pick one of those calculations anyway, so I might as well take them all on to completion. Anything else?
No, I think I'm good.
All right, I do have one more problem, but I'll kind of see where your mental kind of energies are at. If you wanted to work through one more problem, or if you feel like I've had enough and I'm all done with trying to do stoichiometry.
I think I'm good.
Okay. All right. Did you want to ask any questions about the exam? I think I do have sort of the exam key that's available here. So if you wanted to look at anything for the exam, or if you're good, then I'm probably going to have, if you want, you can sign off. I still might continue this video and just kind of walk through the exam just for a minute in case that was any reason that people were tuning in.
No, I think I'm good. Thank you.
Okay, go ahead. You can sign off then. I'm going to keep this video going just so that I can kind of talk about the exam here.
All right. Have a good night.
All right. We'll see you, Courtney. Thanks. All right. So for anybody who was hoping to kind of see the solution for the exam, I'm going to go through it fairly quickly just so that I can get through in like the 15 minutes that I have left here. But feel free, if there's any questions that you have on things, feel free to sort of reach out. So the first 2 pages of the exam were short answer. There is no partial credit given in this section. So I think most people did pretty well on this ionic or covalent piece, remembering that if you have a metal and a non-metal, that's always going to be ionic. Don't get tripped up that you can still have an ionic compound if you've got polyatomic ions that are there. So you don't have to have a metal. For example, if you had ammonium chloride here, that would still be an ionic compound because you have a cation and an anion. It just happens to be a polyatomic ion. couple people missed things here. Important pieces to think about were what the units were for your answer, and then how many significant figures. So some people kind of didn't get the units right here, looking if you're taking grams and then dividing it by grams per liter. That ends up giving you units of 1/1 liter, which ends up giving you units of liters. So if you didn't have the units and the significant figures right, you needed to have, everything kind of right here. So I think a number of people missed some things there. Highlighting here, how you figure out significant figures is different, whether you're doing multiplication and division, and then you look at sort of your weakest link, if you will. It's whoever has the fewest significant figures. So in this case, it's 3. Now, when we're looking at things for subtraction or addition, we need to say who has the fewest number of significant digits to the right of the decimal place. And that limits us. So there's 2 to the right of the decimal place, 4 to the right of the decimal place, and 1 to the right of the decimal place. So we are limited by only having 1 digit to the right of the decimal place. It's not total number of significant figures when we're doing subtraction and addition. Okay, so I think a lot of people got tripped up on that part. A number of questions here with isotopes. So I think a lot of people did fairly well on this guy, remembering that the number of protons plus the number of neutrons is what gives us the atomic mass, which is what we see there, either 63 or 65. If it's copper, then it's going to be atomic number 29. Again, most people did okay on this part. This was a little bit of a sleuthing piece, recognizing that if something has a charge, it's going to have an unequal number of protons and electrons. That's what gives rise to that charge. Let me see if there's anything else sort of tricky here. This one had to have both parts here in order to get full credit. I needed to know this chemical symbol as well as what the atomic mass is. And that atomic mass is really the sum of protons plus neutrons. A number of people got tripped up by this second problem here for our nuclear equations. And this is the formation of neon 20. That means this direction of the equation is important. I think some people maybe had the right pieces to this equation, but it was flipped in the wrong direction. And it's like, well, that's not what our words are saying. We're doing beta decay, meaning this beta particle is a product. We're forming neon 20, which means neon 20 is a product. So the direction, this is not a reversible process. It's a one-way arrow. So the direction is important, and we're indicating whose reactants and whose products. Kind of some combined skills with this little problem here. You needed to know what the nitride ion was, N3-. And then knowing that nitrogen, if it was just its atom, would have 7 electrons. And so we're going to add 3 electrons to it to make it have 10 electrons. And so that was the answer to that guy. All right, moving on to the naming piece. And yeah, a lot of you have said that nomenclature is your nemesis. It's your Achilles heel, but you have to become proficient at it. This is a thread that will continue throughout the entire course. So you have to become competent with it. So please, 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 if this is not something that you do well right now, continue to practice, okay? This is one of those things, Dr. Brown and I were just talking today about it. It's not anything that I can really help you with too much. I'm not a big fan of memorization in general, but this is something that you do need to memorize, these pieces, these polyatomic ions, how these processes work, because naming is just one of these integral skills, just like we have with doing unit conversion, which is why we have this important test after we learn those 2 important skills. But for some people, I know there's been a learning curve to that because it's a lot to take in, particularly if it's not something that you've done recently in another class. So I'm not going to take a lot of time to go through much here from this. The only one I am going to mention, and this was something we didn't really talk a lot about. We didn't have any examples, I don't think, in class dealing with hydrates. Okay, but it was something that was discussed in our video. So highlighting that those videos, you need to recognize that those videos are akin to you being in class with me and taking notes and learning about things. And then what we do in class is we work on problems. So if you want to sort of mentally compartmentalize it and say, well, if she has me watch a 20-minute video and then we do 50 minutes of problems in class, break it up and say, all right, imagine I was with her for 20 minutes and then we only did 30 minutes of problems in class. And then that last 20 minutes, well, maybe it's something I would be expected to do on my own. And I think expecting you to do problems on your own is much more challenging than expecting you to sort of listen to lecture and take some notes and understand things. So this one was part of that video. You need to know what magnesium nitrite looks like. So this is magnesium nitrite when we have a hydrate. And I think many of you have been in lab and kind of done the hydrated salt lab. This means trihydrate, that there's 3 water molecules associated with that magnesium nitrite. Okay, so feel free, you can ask me questions if you have any questions on these nomenclature pieces, but nomenclature is not going away. We're going to continue to see it as an integrated skill with parts of our problems. Okay. So performing unit conversions. So these were one-step unit conversions. Here we have sort of a prefix conversion. Here we have an English to metric conversion. If you did not have the correct units or significant figures, you lost a point on each of these. Each one of these is worth 3 points. Here's another one of these problems that we really didn't practice this too much in class, but it was part of videos that you watched. And it's a skill that I do expect you to know. Treat those videos as if it was something that you were in class and you were taking notes on things. I do expect you to know that content. We are going to start doing more problems where we have to do Celsius to Kelvin conversions or Kelvin to Celsius conversions. So you want to know that the conversion of Celsius to Kelvin has to do with a factor of 273.15. If we're going Celsius to Kelvin, we're going to add it. If we do Kelvin to Celsius, we're going to subtract. Okay. Moving through our unit conversion problems. Here's sort of a simpler unit conversion problem, just 3 steps that we have here. So we're taking units of grams per centimeter cubed, and we want to get to kilograms per meter cubed. So it's a prefix conversion to allow us to convert grams to kilograms. And then when we need to go from cubic centimeters to cubic meters, I know the relationship of 1 meter is 100 centimeters, but I have to cube this entire quantity. I still saw a number of people that just put the cube right here with that relationship, and that's not correct. 1 cubic meter is not 100 cubic centimeters. If you want to envision this and imagine it, remember a cubic centimeter is like a sugar cube. Think about how big a sugar cube is. Think about a cubic meter. That's like a box that's 3 foot by 3 foot by 3 foot. Do you think you can fit more than 100 sugar cubes in that? Absolutely. So that's a reminder that we need to have this cube applied to everything in there, the unit and the value. All right, problem number 12 was almost identical to a problem that we did in class. It's using measurements to determine the volume of a cube. Okay, so length times width times height is going to give you the volume of this. Now, it gives us the volume in terms of cubic millimeters. So again, you could handle this problem one of 2 ways. You could get first to cubic millimeters and then use a unit conversion to convert from cubic millimeters to cubic centimeters. Or if you wanted, you could first convert your length, width, and height to centimeters and then do your determination of volume. But regardless, you needed to know that density is a relationship between mass and volume. The mass is provided for us, and so you're going to divide by your volume. Again, my way that I did this is I determined my volume in cubic millimeters, and then I did one of those prefix conversions that allows me to convert centimeters to millimeters, but I need to cube the entire quantity to get a value that's 10.537, rounding to 3 significant figures, right? I'm limited by this guy. Gives me a value of 10.5 grams per cubic centimeter. That was most of the problem, but then you also had to use this table over here to try to identify who this might be, okay? And so this is most consistent with silver. Now, I did give partial credit if you did the wrong math, but then you chose something that was consistent with that, you still got credit for recognizing that your data said this, okay? But you would have lost points on doing an incorrect calculation. Okay, another unit conversion problem here. This one has a few more steps. Okay. One of the things I noticed is that some people didn't kind of take this on all the way. They maybe stopped at grams here. They didn't have these last two steps. So I could not give full credit for this problem. But this problem tells us that we've got 36 bottles of NyQuil. We know that each bottle has 177 milliliters. And we know the density of the solution is 1.497 grams per cubic centimeter. Okay, so I want to know how many pounds a case of 36 bottles weigh. So again, the way I like to think about this is start with something that you know, like 36 bottles, and I ultimately need to get to units of pounds, okay? Because this question says, how many pounds does this weigh? So pieces that I can put together allow me to walk. I want bottles to go away. I know one bottle is 177 milliliters. Here's one of our magic unit conversions. I can change from volume in a liquid measurement to volume in a distance measurement by using this special relationship. So now I get to cubic centimeters. My density allows me to walk from cubic centimeters to mass. I need to get to kilograms here. And actually, you don't have to get to kilograms if you used a relationship that allowed you to relate grams to pounds if you had that. I don't think the information provided allowed you to do that. So I needed to go from grams to kilograms, and then kilograms to pounds was the English to metric conversion that was provided. Always keep all your significant figures till you round at the end. I've got 3 significant figures because I'm limited by this 177 milliliters. So that case of NyQuil is going to weigh just over 20 pounds, so 21.0 pounds. Okay. I promise you, I am going to give you problems that sort of make sense logically. So those of you who got numbers that were super large or super small, I'm not going to give you something that you won't be able to do a logic check with. So, hey, does a case of NyQuil weigh about 20 pounds? Absolutely, that makes sense. All right, 2 more problems here. This and these last 2 problems were a little bit more challenging, but again, I'm always going to have some problems that are relatively easy, but I am going to give at least one. And in this case, there was part of this problem that I thought was a little bit more challenging. We'll talk about what it is here. Okay, you had a picture here. One of the things, and we talked about this a few times in class, when we see these pictures, they're called molecular scenes. So this is something that shows us molecules. It kind of looks at them like if you had a microscope and you were looking at the atomic level of what's going on. So I can see that I've got some different gases that are here. And importantly, these molecules show me the connectivity. So in this case, I can see that the 2 nitrogen atoms are connected together. And that's important because you only got half credit for your Lewis structure if you put oxygen in the middle. And the way that you know that oxygen is not in the middle is because you had this picture. Okay, so if I look at the picture here, that tells me that I have NNO, but again, our chemical formula basically just tells me the molar ratio of those species. So it's going to be N2O. I would call this guy dinitrogen monoxide. And then here's the molar mass of that. So again, it was 6 points total, 1 point each for all of these pieces. Okay, this guy over on the right, I've got 2 chlorines and 1 oxygen. So we would call this dichlorine monoxide. I did give credit if you put the oxygen dichloride, if that's what you said, because this one was a little bit difficult and challenging to sort of figure out who maybe went first, who was the cation and who was the anion. So I did give full credit for that just in terms of this naming piece, because that was a little bit challenging. But with regards to Lewis structures, again, it was important that you had the oxygen in the middle of this Lewis structure. So I think a lot of people got that one correct. Now this one was a little bit more challenging. So again, if you put your oxygen in the middle, I only gave you 2 out of the 4 points for that because you had a piece of information with that picture that would tell you who was in the middle. If you drew something that looked like this, this has an incomplete octet for that nitrogen. Remember, every atom likes to feel that it has 8 electrons around it. So that's a problem if we don't have that. How you fix that is these electrons are going to end up being shared there. Okay, so this is the best Lewis structure that we can kind of draw there. Okay, So if you have something that you wanted, I know there's a couple people who said, well, I had something else. And if you'd like to know maybe why it was not an ideal structure, just send me a picture of it and we can sort of talk about it. Okay, last problem here, and I have 1 minute before it's 9 o'clock and we've kind of gone over. This was a challenging problem. This was actually a problem that Dr. Brown had on his exam. So it was something that we all kind of said, hey, I'm curious what students can kind of take this challenging problem and run with it. So I've got a sample of a diamond and they sort of tell me its density. And they tell me that an average carbon atom weighs this. And if I've got a little sample of that, if I've got a little sample of this diamond that has a volume of a cubic millimeter, I want to know how many atoms there are. Okay. So again, pieces that we have to string together. Always start with the piece that you know. All right, I'm going to start with micrometers. I know that that little piece of diamond, it has a volume of 1 cubic micrometer. Now, I need to somehow get to number of carbon atoms. So notice that's what I want to have up here in the numerator of my last unit conversion piece. Okay, so I can take micrometers and go to meters. That's a prefix conversion. I can go from meters to centimeters. And why it's important to go to centimeters, and notice here it's cubic centimeters, but why it's important to do that is once I know the volume of my diamond in cubic centimeters, I can use my density to walk to a mass of diamond. And then once I know the mass of the diamond, one piece of information told me how many grams 1 carbon atom was. So stringing these unit conversion pieces together allows me to get the number of atoms that are in that little tiny crystal of diamond. Okay, so some people, okay, they saw this, they saw the how many piece, and this was like, this was, I'm not intentionally sort of tricking you, but it's something, this wasn't an Avogadro's number piece. Okay, we didn't need to use Avogadro's number because we already had something that related number of carbon atoms to mass. So that's the piece that we needed to use. But I think a lot of people who work through this problem are people who are really good at unit conversion and can figure out the unit conversion pieces and figure out how do I stack these things together? How do I line them all up? So I take units that are given for the problem and convert them into units that I want for my answer. All right, so that's a quick run through of the exam key. Please let me know if you have any questions. And again, that was the end of our unit 3 here on stoichiometry.